And then you have what is the null space of a matrix. What is a null space of a matrix? So if you have an m by n matrix, null space is the set of all x in Rn such that Ax is equal to 0. Right? The solution space of the homogeneous equation Ax equal to 0. Right? And the dimension of this space, we call it to be the nullity of a matrix. Next, what is rank nullity theorem? Rank nullity theorem says that if you have an m by n matrix, rank of A plus nullity of A gives you the number of columns of the matrix. Okay, nullity, if you know one of them, either rank or nullity, then you can identify the other using this rank nullity theorem. Okay, fine. Then we saw what are linear mappings, right? What are linear mappings? So linear mappings are functions from Rn to Rm which are defined in this way, right? F of x1, x2, xn is defined in this way. For example, we saw how it looks like for R2 to R3, right? So we see that linear mappings means always we have f of x is equal to Ax. Okay, so where A is this matrix. Okay, and we saw that it satisfies these properties that f of x plus y is equal to f of x plus f of y, and f of alpha x is equal to alpha times of f of x for any alpha in R. Okay, so this is the linearity property of a linear mapping, right? And we saw one example for that. So let us see how many of you can answer these two questions based on the topic we have seen in the previous session. So we have seen an example just very similar to this. Read this question, take a minute. Very similar to the previous one. So you have the rates of pen, water bottle, toothbrush, and toothbrush and chocolate as 10, 40, 25, and 20 respectively. Now, if T of x, y, z, w denotes the total cost of x pens, y water bottles, z toothbrushes, and w chocolates, which of the following will be the correct expression for T of x, y, z, w? Yeah?
The
D,
last
ma'am.
option, obviously.
Okay. Right, all of you can see that why D is the correct option, right? Yeah. So you see that. So for example, if someone is buying one pen, two water bottles, so three toothbrushes and one chocolate, then you know you have to put 10 times of 1, 40 times of 2, 25 times of 3, and 20 times of 1, something like that. Right? So this is the correct formula. Good. What about fifth question? So fifth question is an MSQ. So you can tell me what is the
B,
correct option.
BC, ma'am. Fifth question.
Okay, so let's see. So you
413,
have,
B and C.
yeah, so 3 pens, 5 water bottles, 10 chocolates, and you see there are no toothbrushes. So chocolate corresponds to the W variable. And so in place for Z, there is 0, right? So T of 3, 5, 0, and 10. And what is the value of this? You have to substitute it here, right? So if you substitute it in this formula, you get 10 times of 3 plus 40 times of 5
5,
plus
G,
25 times of 0 plus 20 times of 10.
10.
So you have 30 plus 200 plus 0 plus 200. So 430. Right? So these two questions are clear for everyone, right? Yeah?
Yes, ma'am.
Okay. So now let us look at the general definition of a linear transformation. A function t from v to w between two vector spaces v and w is said to be a linear transformation if for any two vectors v1 and v2 in the vector space v and for any c in R, the following conditions hold. T of v1 plus v2 equal to t of v1 plus t of v2, t of c v1 equal to c times of t of v1. Now, do you know already some example for a linear transformation? Have we already
Yes,
seen
ma'am.
some function which satisfies the condition? Yes, right? So we have seen that if you take a function from Rn to Rm, you already know that Rn and Rm are vector spaces, right? And if you define the function in this way, then you know that this function is already satisfying the linearity properties. So this is a linear transformation, right? Okay, so now instead of V and W, can we have some other vector spaces here? Instead of, instead of Rn or Rm, can we have some other vector spaces? Can you think of some other vector spaces?
Ma'am, V and W is a general form, na, so how we can.
No, no, I'm asking
Like,
one
like
point
we can, we can trace any vector space in it.
Euclidean space. I'm asking, apart from Euclidean space, can you recollect some other vector spaces? This is my question.
Matrices, maybe?
Okay, can you specifically tell? If you just say matrices, it does not make sense. You have to be specific. What is your V and what is your W?
Ma'am, M 2 cross 2, like that, something. And
Okay,
then
2 cross
maybe,
2.
yes, then
Okay,
we can just define maybe transpose of the matrix can be a function.
okay, okay, fine,
I
good.
I don't know
Yeah,
if it will be the
function, that is next level of question. So just first of all, I'm checking whether you recall any other space vector spaces other than Euclidean space. Good. Matrices, of course, is the other thing which you can think of, right? Okay. Of course, you can also take subspaces of the Euclidean spaces. That is obviously there, and then you can take subspaces of the matrix spaces, right? Okay, good. Okay, so now look at this mapping T from R2 to R2. Now it is defined in this way. Now, is T a linear transformation? What's your answer?
Yes.
Yes, right? Because does it resemble this kind of a equation format? Yeah, it's in fact a linear mapping, right?
yes, ma'am.
Right? So you see that it is specifically of this form T of x comma y is equal to 2x plus y time, and the next component is x minus y. Right? So you know that how can we write it in terms of matrix? You already know that. How can we write? Can you tell? What is your A?
Any column or row matrix?
So can you tell what are the columns for the matrix? So you see the columns of the first column is the coefficients in the first component A11. Sorry, it's the coefficient of the first component x1, first variable x1, A11, A21, A31, and so on. And then the second variables coefficients form the second column that way. So here the coefficients of the first variable is
2 and
2,
1.
2,
1.
1, and 1 minus 1.
Yeah, times of x comma y, right? So you see that here if you multiply you get 2x plus y and then x minus y, right? So you see, you already know that if a function is of this form, then it is linear. You already know, right? So the answer is yes for this, right?
Ma'am, could you elaborate this? Could you just prove the two conditions, one scalar multiplication and addition?
Okay,
Yeah,
okay, fine.
could you
So
please?
let us
Yes.
take a vector u. Let's call it x1, y1. Let's take a vector v, which is x2, y2. All right. So now you have to say T of u plus v is equal to T of u plus T of v. Now what is u plus v? U plus v is x1 plus x2, and v and then here second coordinate is y1 plus y2, right? Now T of u plus v is equal to, according to this, what you can say, T of x1 plus x2. So you should put x1 plus x2 in place of x. So 2 times of x1 plus x2, and then in place of y you should put y1 plus y2. Same thing for the second component, x1 plus x2 minus y1 minus y2, right? So now you have to just split it and write. So 2x1 plus y1. We are just rearranging the terms. 2x2 plus y2, comma, x1 minus y1 plus x2 minus y2. Okay. So now you can again split the terms. So 2x1 plus y1, comma, x1 minus y1 plus 2x2 plus y2, comma, x2 minus y2. Now what is your first term? Your first term is nothing but t of u and the second is t of v. Clear? Yeah.
Yes, ma'am.
So the same thing you can do for scalar multiplication also. So you have 2 times of alpha x1 plus y1, sorry, alpha y1, comma, alpha x1 minus alpha y1. So alpha is common from all the terms, so you can take it out. So you get 2x1 plus y1, comma, x1 minus y1, which is alpha times of t of u. Then, so t is linear. Okay. By the
Ma'am,
way, yeah.
ma'am, above you have in the second line tx comma y is equals to ax y above in the second line.
Mm-hmm.
Yes. How you concluded that this is linear?
Because this is what we have proved here. If f of x is equal to ax, then it is linear. We have already proved it, right?
Okay. Okay, ma'am.
Yeah.
Okay, ma'am, got it.
Okay. Okay. So in general, if t is from R2 to R2. So this is a map from R2 to R2, right? Now tell me, what is the general format? General linear transformation from R2 to R2. Can you tell me how does it look like? Instead of numbers, I just want you to give some A, B, C, D. That's all. Tell me.
X comma 2x plus.
No. I don't want numbers. Instead numbers, I just want A, B, C, D.
Okay, ma'am.
Try it and tell me.
Ax minus y minus by
Plus Y is
plus
more general. Yeah.
I think we have to give some x1 or x1 and y1, right? Because it is R2, so every vector.
Yeah, I am taking X comma Y, right?
Yes, ma'am.
Mm. These are the two components. Then what can be the second?
cx plus dy.
Plus dy.
That's all, right? Yeah. And you know that you can
Yes,
write it
yes,
as
ma'am.
A, B, C, D, X, Y, right?
Yes,
So this
ma'am.
is for any R2 to R2. So you don't have to verify anything. If you see there is a mapping from R2 to R2, which is of this format AX plus BY, CX plus DY, where A, B, C, and D are real numbers. Okay, so if you see any mapping which satisfies this condition, then straight away you can say this mapping is a linear transformation. Okay, fine. Now,
Okay.
Now, I am going to tell one important property. Before that, giving that property, I want to ask a small question here. Okay. So,
Yes, ma'am.
what is, suppose T from V to W is a linear transformation. What is T of 0, comma 0? You don't have to know what is exactly T. But without
Zero,
knowing
ma'am.
itself, why it is
Zero.
0? Yeah, some of you are saying 0. Can you tell why?
Because you have to just replace x and y
Since
with.
it is multiplying with ax by.
I don't hear anything clearly. Can maybe one by one you can say, yeah, someone tell me.
Then since x and y is 0 only, then whatever the coefficient a, b, c, d will be, then it will become 0 only.
By the way,
Ma'am, the zero should be
R2
preserved.
to R2. I'm asking for any V to W. Any V to W, how will you argue?
The zero should be preserved, ma'am.
Why? Why it should be preserved? Okay, I
So
will
as to
give you a
maintain the
hint.
linearity.
Yeah, that is the hint. You have to use either of the properties. Either you use T of U plus V equal to T of U plus T of V, or you use T of alpha equal to alpha times T of U. So you use one of this property to explain why T of 0 comma 0 is 0 0. Anyone? Okay, let's say you are having two vectors U and minus U. Now what is, now T of 0 I can write as U minus U. Yes or no? Right? Now what is
Yes, ma'am.
T of U plus T of minus U? Now according to the scalar multiplication property, I can bring out this minus 1. So this becomes T of U. So this is 0. You agree?
Yes, ma'am.
Yes.
Yes, either you can prove it like this, or if you want to use scalar multiplication, then you can argue it this way. So you take alpha to be the 0 vector. So 0 times of U. So this is T of 0, right? T of 0 is T of 0 U, you can write. And 0 times of TU. So if you multiply any vector with 0, you are going to end up with 0, right? Yeah. So either way, you
Yes,
can
ma'am.
see that the 0 vector is mapped to 0. So what is the important fact you have for a linear transformation T from V to W, where V and W are vector spaces, T of 0 equal to 0. That is, image of the 0 vector of V is the 0 vector of W. Is that clear? Yeah.
Yes, ma'am.
What does this 0 mean? You should understand it from the context. Okay, so this 0 represents the 0 vector in your domain V. This 0 represents the scalar 0. This also represents the scalar 0. This 0 represents your 0 vector of W. So what is each of the 0 telling? That you should have a clear understanding, right? Okay, that depends on the where, what is the position of your 0, you should have an idea. Okay, fine.
Ma'am, that coefficient one logic can be applied to Rn also, no?
What? Which logic?
If x and y is zero, the coefficient, whatever coefficient we will multiply, we will get and then zero only.
This one.
Yes, ma'am.
Of course, this U is any vector from V. So your V can be any vector space. So of course, Rn you can apply. Okay.
Yes, ma'am. Yes, ma'am.
Okay. So here are some examples you see. Just have a look and see whether all of them are satisfying the property of linear transformation. How will you check whether they satisfy the property of linear transformation? Have a look and tell me if you have any doubts of how to conclude whether they are linear transformation or not.
Now we do just check the addition and scalar multiplication, right?
That is the like, yeah, of course, applying the definition method. But I told you, see, when if you have T from
We
R2
use
to
two
R2, you don't
methods.
have to go all do all these steps. You just have to see whether you are able to see it in this format, or at least for R2 to R2, you know that this is a specific format, right?
Okay, got it. Yeah.
So can you all tell what is the specific format for each of these cases? So from R2 to R2 we have already written. So T of x comma y is equal to ax plus by cx plus dy. So what is your A, B, C, D?
A is 2.
A
A
is
is 2,
2.
A equal
B
to
is
2,
0,
B is 0,
0, C is 0.
C is
B and
0, D
D are
is
all
0.
as 0. Yeah.
Okay. Now you are going to tell me the format for R3 to R3.
Hmm.
Tell me.
So yeah, so
AX,
we'll take
AX,
6
BY,
variables.
Yeah. AX.
BY,
I guess
CZ.
we will run out of variables soon. So maybe I'll write
Yeah.
A1x plus B1y plus C1z. Yeah, now tell
Z,
me
comma
Well,
A2X, B2Y, C2Z,
B2y plus C2z.
C2Z.
Yeah,
A1 is here, ma'am.
plus B3Y plus C3Z.
plus C3Z.
Okay. So in this specific case, can you tell me what are your A1,
One
B1?
is
A1 is
A1 is 1 by 2,
2 by 2. 1 by 2, sorry.
B1 is 0,
Zero,
C1 is 0,
0,
A2 is
0.
0,
B is B2 is
B2
3.
is 3, C2 is 0, A3 is 0, B3 is 0, C3 is 5.
very good. Okay, good. So same way, tell me what is the general format for T from R3 to R4. T from R3 to R4.
And say T x comma y comma z is equals to A1x B1y C1z plus D1
Plus what? Will there be a plus? You have only three
No,
variables.
no
No,
plus.
only
Plus
tables. Yeah,
yes,
comma.
yes,
Yeah,
ma'am.
So what should come here?
comma.
from
Then
A2X
A2x A2y C2z.
B2Y plus C2Z.
Here
A3
A4 till A4 will come.
yeah, you will have before, right?
Yeah.
Yes.
Sorry, sorry. So this is y and this is z, and then you have a4x plus b4y plus c4z, right?
Yes.
So
Yes.
here you can see and match. So here what is a1?
A1 is 0. A2 is 4. B1, sorry, B1.
B1 is
4. C1 is minus 1.
yeah,
A2 is 0. B2 is 3. C2 is
11.
plus 11 by 19.
yeah.
Yes. Then
This yeah. A3 is
A3 is 5. B3 is minus 2. No, 0. C3 is minus 2.
and a4.
A4 is 0. B4 is 23. And C4 is 0.
So you can see that each of this is satisfying this kind of a format, and you are able to predict the format. We just have very two more simple cases. Let us see T from R to R3. So if T is from R to R3, what is the format?
Is T of x, no,
P1X is
is equals to
A1X plus
uh,
Ma'am, just A1x.
A1x plus A2x,
Comma.
B
A2X.
Just
A2x.
comma.
Just comma, right?
Just comma.
Yes,
comma
just comma.
And then
A2x,
B1X
A2x
A2X
plus
A3X.
A3x.
not plus comma
Plus,
A3x,
yeah, sorry,
right?
A3x.
So you have something like this. Okay,
Yes, ma'am.
fine. Now, what about, so in this case, you see that A1 is 1, A2 is 3, and
3,
A3 is 23 by
23,
89.
89. Yes,
So,
ma'am.
does it make any difference if we are changing the variable? Here, the variable is T. Will it make any change in the transformation?
No, ma'am.
No,
No.
right? Yeah.
Mm.
No transfer changes.
Yeah. Now, what about the general form for R2 to R?
TX
X comma
T
y
y
is
equal
equals
to A1x
to
plus B1
A1x plus
only
y.
that
plus
one term. Yeah.
That's all, right?
Yes.
So
Yes,
now you
ma'am.
know that if T from Rn to Rm, for any Rn to Rm, you know how to write the general form, which is the first thing we saw, right? This is the general form, right? So if you have specific cases, by now you all should know how to write the general format so that you can easily compare and see whether it is really a linear transformation or not.
Ma'am, can you please repeat that R to R3 once again, ma'am? Sorry. The T
R2
of,
to R3.
yeah, the transformation which you written last.
Oh, here. This one R2, R3?
Yes, ma'am.
Okay. This one.
Yes, ma'am.
You want me to explain or?
Yeah, yes, please.
Okay. So here you just have X, right? Only one variable you are having, right? So you don't have Y, you don't have Z, right? So all these terms are just disappearing. That's all.
Oh, okay. Okay. Yeah.
Fine. Okay. So now look at this question. Let us consider the standard basis 1001 of R2, right? Define the linear transformation as follows. This is a very important question. Everyone listen carefully. Okay, this is an important question. So T from R2 to R2 is defined using the standard basis. This is your standard basis, and they have not given what is your T of X comma Y, but they have given the images of your standard basis. Now they are asking us to find the explicit definition of T. It means what we need to find, that is find T of X comma Y, the expression for T of X comma Y. This is our question. Now, how will you find T of X comma Y? Any idea?
No, we will
Try
try to write in a standard form.
Yes.
2x comma 0.
Yes. Right?
So
So
not
first step is,
2x comma y.
yeah. So first step is, right? So let us say that this is your E1, this is your E2, right? So step 1 is that, so you write X comma Y in terms of E1 and E2. So what are your coefficients alpha and beta here? This is a very
Alpha will
straightforward.
be
Alpha
Alpha is 2,
is 2.
beta is 1.
Don't be like going too forward. The question is not there yet. I'm just asking X comma Y.
1,
Yeah,
comma
alpha
2.
comma beta, right?
Alpha 1 comma 0.
Yeah, so this is alpha.
Alpha comma beta, right?
What is alpha and beta? I'm asking.
So what?
alpha is even by x, no?
Alpha is X,
That part.
just X. Yes. X E1 plus Y E2. That's all, right?
Okay.
Yes,
Yeah.
ma'am.
Okay.
Yeah.
That's fine.
So next step 2, we are applying T on both sides of this expression. So T of X comma Y is T of X E1 plus Y E2, right? And then you can use the linearity condition and split them, T of X E1 plus T of Y E2. Now X and Y are just real numbers, so you can bring them out. So X times T of E1 plus Y times T of E2. Now what is T of E1? What is T of E1?
2 comma 0.
Right? This is TE1, this is TE2, right?
Yes.
Yes, ma'am.
So Y times of 0, 1. So which is nothing but 2x comma y,
Plus.
right? So your T of X comma Y is 2x comma y. Is that clear? So if you are just given the basis, the images of the basis for a transformation, the first step is that take a random vector from the domain, okay, and then express it as a linear combination of the given basis. In this case, it is the very easiest one. And then you apply transformation on both sides and then use linearities to split them, and then you apply the values of the transformation given to you and simplify to get the final answer. Okay, are the steps clear?
Ma'am, could you explain step 1 once again?
Step 1, I am taking a general vector x comma y from my domain. I am trying to express it as a linear combination of the given basis. And then I have to find what are the coefficients for the general element with respect to the given basis. This is my step 1. Okay? Clear?
How you have written that x E1 is equals to alpha E1 plus beta E2?
Okay, what is the definition of basis?
basis, ma'am, linearly independent
And
and minimal
it
spanning.
is a spanning set for the space, right? So it spans. What is
Yes,
the
ma'am.
meaning of span? You take any vector from the vector
Or
space.
linear combination.
Yeah, you take any vector from the vector space, you will be able to write it as a linear combination
Linear combination.
of elements, right? So that
Yes,
is
ma'am.
why I have taken a random element. I know that E1 and E2 is a basis, so I
Ma'am,
will be
till
able to.
alpha beta, I've understood how you have compared it to x e1 plus y e2.
Okay, what is alpha E1? What is alpha E1 plus beta E2? Alpha times of, see, in math, whenever you don't understand, you just have to write it out and see. What is E1? You write it down. What is E2? You write it down. What is that you are getting? Alpha times of 0
Alpha.
plus 0 times of beta, 0 comma beta, which is alpha comma beta. Now x comma y is equal to alpha comma beta, which gives you x is equal to alpha, y is equal
Okay,
to
ma'am.
beta. That's all, right?
Yes, ma'am.
That is why I have taken alpha is equal to x and beta equal to y. Got it?
Okay, ma'am. Yes, ma'am.
Okay. Okay, clear?
Yes, ma'am.
Okay, fine. Okay, so now everyone look at this carefully. Now you are going to tell me what are the steps. I have already given you the steps. So here you have a similar problem. Look at it carefully. So instead of E1 and E2, now you are having some other different bases. So let's say V1, V2. And you are given that this is a linear transformation and the images of this particular basis are given. So what is your first step? What is your step 1?
Taking a random vector x comma y.
Yes, from the domain.
Then, yes,
And
ma'am, from the domain R.
then
Then alpha times of 1 comma the e1
yeah,
plus beta times of 1 comma 1 vector.
yeah,
And then comparing with x comma y.
yes. So here how will you compare? First let's simplify and write. So this is alpha comma 0 plus beta comma beta. So which simplifies to alpha plus beta comma beta. So now we have to compare it with x comma y. So if we compare, we get x is equal to alpha plus beta and y is equal to beta.
Beta. Yes,
Okay.
ma'am.
So it means
Yes,
what?
ma'am.
So you know what beta is y. So what is your alpha then?
Alpha
Exit.
x minus y, no?
X minus y.
Yes.
Right? See, remember, you have to, here in this place, you have to express the coefficients
In terms of x and y.
y. That is what we need to do. Okay. So we will get x comma y is equal to x minus y times of v1 plus y times of v2. Is that fine? In place of alpha, I have written x minus y. In place of beta, I have written y. So I am just replacing the coefficient in terms of x and y. Is that clear?
Yes, ma'am.
Okay, fine. Now the next step, what is the next step? Tell me.
Applying the linear transformation steps.
Right? So you have x minus y times of tv1 plus y times of tv2. I have straight away applied the linearity property and wrote it. Is it fine or should I write the steps? If anyone don't understand how I wrote this straight away, please ask me. Is it clear or should I explain?
Ma'am, could you please explain, ma'am?
Yes. Okay. So here I am applying t on both sides. Okay. So now you see that these two terms are scalars. This is a scalar and this is a scalar. Right? So scalar means you know that you can bring it out. So before that, first of all, addition, I am just splitting using the first linearity property. Right? And then since they are scalars, I know I can use property 2 and write it in this way. Okay. Now what is TV1? Here actually it is F. Everywhere I have written T. So maybe I can change it to F. What is your FV1 and FV2?
1 comma 0.
No. FV1.
Oh, FV1 2 comma 0 and 1 comma 1
Okay.
after transformation.
So you
Yeah,
get 2x
2x minus y comma y.
y plus y and then comma. Here
Y.
you will get just y. Correct? So
Yes, ma'am.
you get 2x minus y comma.
Minus y comma y.
Fine. So if you want to just cross check whether you have computed it correctly, you just have to simply apply this 1 0 and 1 1 and check. So what is, so this is f of x comma y. So what is f of 1 0 in this way? Check it.
2 comma 0.
And what is f of the second one is 1 1, right? Yeah.
1 1.
Yeah.
Yes,
What
ma'am.
is f of 1 1?
It's 1 1 only.
1 1 only. Right? So you know that whatever you have found is correct. So this is a verification step. This is optional. If you want, you can verify. Okay? Clear?
Yes, ma'am. Yes, ma'am. Clear.
See, if you are given a transformation and the images of the basis element, first you take a random element from the domain, express it as a linear combination of the given basis, express the coefficients of the basis elements in terms of the variables in your vector. Okay? And the next step,
random
apply
element
linear
equation.
yeah?
Yeah, we just express the coefficients in terms of the random variables we took.
Yes. And then here you are applying linear transformation on both sides. Apply the linearity property and then substitute the given values of the linear transformation. Simplify, get the final answer. If you want to check your answer, you can verify it using the basis given to you. Okay, fine.
Yes,
Okay,
ma'am.
so what is the observation? If you have a transformation T from V to W, it is enough to know the images of the basis elements of V to get the explicit definition of T. You understand the importance of the basis. Basis helps us to understand the whole vector space. That itself is a big thing. If you have basis, you can express any vector using the basis element. Now, you are able to even define the whole linear transformation by only defining the images of the basis element. Okay?
But can you just show the answer once again? I don't mind.
2x minus y comma y.
Okay. Okay. Thank you.
Okay. Now let V be a vector space and let x not equal to 0 be a fixed vector in V. Okay. Is the translation function f from V to V defined by f of V equal to V plus x a linear transformation? So I want you to think about this. What don't answer. No one please answer now. Let me complete the question and then you answer. You may answer it in so many different ways, but I want you to answer in this way which I'm asking now. So you have to you should not use any linearity property straight away. You should give an argument without using linearity property. Can anyone try that? You should not use f of v1 plus v2 is equal to f of v1 plus v2 or f of alpha v equal to alpha times f of v. These two properties you should not use to answer this. You can of course answer, but for now, try to answer it in a different way. I have given you an important property of a linear transformation. You can use that. This is the hint. What is
F of
the
zero, f of zero vector will also be not zero then.
Exactly. So f of 0, what happens to f of 0? If you take v to be 0, then f of 0 is 0 plus x, which is x, and it is given that x is non-zero, right? So it means f of 0 is not equal to 0. So it means, can it be a linear transformation?
No, ma'am.
So you can see that f is not a linear transformation. Okay. Of course, you can also see it using the definition. So using the definition, f of v1 plus v2, what is, according to this, it is v1 plus v2 plus x. And what is f of v1? v1 plus x. F of v2 is v2 plus x. And f of v1 plus f of v2 is v1 plus v2 plus 2x. So you can see that f of v1 plus v2
LH is
not equal to f of v1 plus f of v2.
plus V2.
Same you can do with scalar multiplication also. F of v, you know that it is v plus x. Now what is f of alpha v? Alpha v plus x. Now what is alpha times f of v? It is alpha v plus alpha x, which is alpha times of v plus x. So you can see that f of alpha v is not equal to alpha f of v. So either you can use this, or you use this, or you use this. That is sufficient. If you want to use everything, that is up to you. But one condition is enough to say that this is not a linear transformation. If one of this fails, then you know that it is not a linear transformation. Clear?
Yes, ma'am.
Okay. So,
Can you explain this property once?
which one? This
V is
question.
equal to, yeah, first one, ma'am.
See, here I have just used the property that if f is a linear transformation, the zero vector of the domain is mapped to the zero vector of the codomain. So that property I want to use here. So I am seeing what is the image of the zero vector here. The image of zero vector is x, which is given to be non-zero. So the image of zero, so the zero vector of the domain is not mapped to the zero vector of the codomain. So it is not a linear transformation. Fine?
Yeah, ma'am, fine.
Okay. So what is the question here? I've just written a map. What is it I want to do with this? What is the next question? Okay, I have some mapping here. Of course, you know that this is a linear mapping, right? We have seen examples for this, right? This is a linear mapping. Oh, no. Hold on. I was just over looking at this problem.
Not linear.
Yeah.
Because you're adding it with a constant, so that's
Yes.
not.
So this is
Yes,
basically x comma y plus 1 comma
-2.
minus 2. So this
Just like the
is actually a
previous question.
translation. So this t is actually a translation, right? So now can this be a linear transformation? Yes or no? Sorry. Is my question clear? Is this a linear transformation? I should have written clearly. So
Now
is
it is just the previous question basically, right?
no,
yeah,
ma'am.
I have
It is
given
0,
specific
0.
v and a specific x. That's all. Is t a linear transformation? No, right?
Yeah.
No,
No, ma'am.
Right? So
0,
here
0
I
is
have
not
taken the v to be r2, and I have taken the specific x given here. The non-zero x is 1 comma minus 2. That's all. Right? So this is not a
Yes, ma'am.
linear transformation.
Can you explain this once again, ma'am, if you don't mind, please?
See, here what is given to you? T of x comma y is x plus 1 comma y. This splitting you understand, right?
Yes, yes.
Okay. So now you see that this is x comma y plus 1 comma minus 2. So now I call this v and I call this vector as x. So you
Okay,
can
okay.
see that this is t of v equal to v
V
plus
plus.
x.
Okay, it's following the earlier one. Okay, fine, got it.
So your capital V is R2. So t is from v to v. x is non-zero, tv equal to v plus x. And everything is exactly the same. Got it?
Okay, okay. Yeah, yeah.
Okay, fine. Okay. So now look at this question. So option 1, you have three vectors u, v and w. Do you see any relationship between these vectors u, v and w?
So minus times of v plus u is equals to w.
They are a linear combination. They are
Linear combination.
linearly dependent.
Yeah, so w is equal to
U plus minus v.
w is equal to u minus v, right?
Minus b.
Yes.
Yes.
Right, w is u minus v. If w is u minus v, then here you are given that t of u, t of v, both are 0. Now what is t of w according to the linearity property?
T of u minus.
That's 0. Yes.
Minus t of v.
Yes, v.
This is a 0 vector, but what is given to you? But,
Non-zero vector.
Non-zero vector.
but given t of w is 5, 1, 0. So not possible.
Yes.
So such a linear transformation is not possible, right?
Yes, ma'am.
So option 1 is incorrect. Clear? Why option
Yes,
1 is incorrect? Clear? Okay.
Yes, ma'am.
Now let's look at option 2. Now you have three vectors u, v and w. Now check with the linear independence of these three vectors u, v, w. Are they linearly independent? How will you
Yes,
check
ma'am.
first of all linear
Yes, ma'am.
independence?
They are linear.
Okay,
Now we'll just make a matrix
Rho
of
is non.
three of them and then so get the determinant of the matrix.
okay.
Determinant.
Okay, so you just find the determinant of this matrix, or you can write row wise, that does not matter, the determinant will not change. So you find the determinant. You got a non-zero value? Yeah?
Yes, ma'am.
So if it is non-zero, you know that u, v, w are linearly independent. If they are linearly independent, does it really matter what are these vectors, what are these images? Does it really matter? Tell me. As long as it is some vector from the codomain, does it really matter what are the vectors? Does it really matter? Tell me, to check whether it is a linear transformation. See, as
Didn't get the question.
now, first of all, you note that u, v, w are linearly independent. It means it is actually forming a basis.
Basis? Yeah.
Yes, ma'am.
It
Basis.
forms a basis for R3. Just now we saw that if you have a basis and you are given the mappings, just the images of the basis, then you can find a linear transformation which satisfy the condition, right? Yes or no?
Yes.
So you know that option 2 is correct, right?
Yes, ma'am.
Correct.
So whatever is this vector given to you, it does not matter what are the values here. You will still be able to find a t satisfying the condition. Okay? Clear?
Yes, ma'am.
Okay. Now look at option 3. Now I'm not going to tell anything. You analyze and tell me. What did I do? For option 3, true or false?
Linearly independent. So
They are linearly independent.
Okay. Option 3, you notice that u, v, w are linearly independent. What next?
so they have to be a linear transformation.
But here you are given an extra condition.
Okay.
Just this one, up to this, it is completely fine. You are given an extra term. So you have to
Yes,
be
ma'am.
careful. Okay.
1 for 2 is linearly independent or not. That we have to check, ma'am.
No. No, no, no.
So to
See,
first form the function first. After that, we have to check whether it is
yes,
working or not.
yes, yes, exactly. See, UVW are forming a linearly independent set. It means UVW is a basis for R3,
Yes.
right? So it is a basis
Yes.
for R3.
And
Now, if it is a
Yes.
basis for R3, you know that any vector 1, comma 4, comma 2 can be written as a linear combination of these basis vectors, correct?
yes.
Yes, ma'am.
Now, what will be T of 1, comma 4, comma 2? Alpha times Tu plus beta times Tv plus gamma times Tw, correct?
Yes, ma'am.
Yes.
Now
And it
what
is
is
also not to zero.
what
So
is Tu? Tu, Tv, Tw all are
zero.
Zero.
0.
Zero.
So
Uh,
alpha times 0, beta times 0, gamma times 0 gives you 0. But what is given to you?
T1
Non-zero.
non-zero.
Yeah, 1, comma 4, comma 2 is some non-zero vector, right? Some non-zero vector. So which is not
2, 4,
possible.
1.
Mhm.
So option
so
is
not a
option 2 is incorrect.
hmm.
Clear? Why option 3 is incorrect?
Yes, ma'am. Got it.
Okay.
Ma'am,
Now,
if we take 1, 4, 2 also in our case to find the determinant, whether it is linear independent or dependent,
first of
will
all,
it?
how will you find determinant for a 3 cross 4 matrix? So here you will
Okay,
have
ma'am.
only 3 vectors. Now fourth vector obviously says that it is linearly dependent, right? In
Yes,
R3,
ma'am.
only 3
Yeah.
linearly dependent vectors can be there.
Okay,
Yes.
ma'am. Yes, ma'am.
Yeah. Now look at option 4. U and V are basis elements. T from R2 to R2. You are given some vector for T of U, some vector for T of V. How is this a linear transformation? Is this a real number?
This is the basis again. So
No,
Yes.
ma'am.
This is not a real number.
no, this is a dual
No.
number.
This is a real number.
Is this a real number?
Yes. Yes.
Yes.
Yes. So you know that these are elements from R2. So
Yes,
is there
real.
anything to check? Is there anything to verify further? You already know that they are basis elements, and
Yes.
whatever the basis elements are mapped to in R2, you can find a linear transformation satisfying the conditions, right?
Yes, ma'am.
So you know that this is a linear transformation. Clear?
Yes, ma'am.
Yes, ma'am.
Okay. So all the options are clear for everyone, right? Yeah?
Yes.
Okay, fine.
Ma'am, please explain option 4.
See, option 4, that is what
Yes,
I
ma'am.
told here already. So see here, this forms a basis. So option 4, you see that U and V forms a basis for your domain R2. Okay, and you are given that T is from R2 to R2, and T of U is given as some vector, and T of V is some vector. What is this vector? Does not matter. Whatever is the value here, the star, 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 star are just some real numbers. Does not matter what are they. Okay, they are just some vector from R2. Then this condition will tell you that T is a linear transformation. Why is that so? Because that is what we saw here. If you have a basis, and if you know the images of the basis elements, then you can find a linear transformation satisfying the condition. That is what we saw. Got it?
Yes, ma'am.
Okay. Suppose V is any vector space. Define a linear transformation T from V to V. You don't know what is your vector space. It is some vector space. So for any arbitrary vector space, your transformation should be valid. So you put any vector space in place of V, whatever transformation you are going to define should be valid. Give such example. Define T in such way. There are several possible ways. Tell whatever comes in your mind. So let us first take some
Taking
random
target
vectors
to
from
it.
V.
We
Yes,
Yeah.
can we can assume some basis for V and do something.
But you don't know the dimension. So how many elements are you going to take and how are you going to
N
define?
n number of elements maybe like.
Okay, so I guess you are going to the next level. So let us not go into the basis and all. I just want to define T of V for any V in V. How can you define?
Taking some random vector x comma alpha beta.
Random?
Random vector x comma y from vector space V.
You
No,
see,
but
what
this is
is
not,
X,
they
Y?
not
You
asked.
don't know. Whether V is R and you don't know. You don't know anything
Okay.
about V.
Okay.
You can just give some constant
Think of,
CV.
yes, yes. This is of course a good example. So CV where C is in R, good example. Maybe even you can refine it. The most easiest one.
V1 plus V2 also you can do, right? For V1 V2 belonging to V.
See what is V1, what is V2, you don't know. Then it does not define. It should be defined for any vector.
Can we use zero vector?
Exactly. So the linear zero transformation, this we call as the zero transformation. All vectors, all V in V goes to zero. Okay, I should write it better. Sorry. So here what happens? All V in V goes to zero. So that is called a zero transformation. Okay. Of course, we can write it like this. If we write it like this, then what happens? T of V equal to V. Then what happens?
C
This is called the identity transformation.
Yes, ma'am, identity.
Right? This is the identity transformation. Okay, fine. Okay. So now you have two linear transformation defined. T of x comma y equal to x minus y. T of x comma y equal to x minus x comma y. Okay. So what is my question? I have not completed it. So, okay, I want to look the. Okay, fine. I got it. So now we have seen what is the abstract things, properties of a linear transformation. Just to see what are the more geometrical way to see a linear transformation, that is what we are going to try next. Okay, how to see the geometrical aspect of a linear transformation. Okay, so I'm going to give you a small task here. Everyone try it and we will discuss it. What you are going to do, everyone draw an x and y axis in your paper. Draw an x axis, y axis. Okay, you do that same for B also. Draw x axis, y axis. Okay. Okay, you are going to take some x axis and y axis. Now you are going to arbitrarily pick, okay, some vectors. Okay, set one from, so this is your first quadrant and second quadrant, right? So maybe set one where I will say y is greater than or equal to 0. Okay, and set 2 y less than 0. For example, I can take the point 1 comma 1, which will be here. I can take the point minus 5 comma 1 or 5 comma 2, which is going to be here, and I'm going to map the images here. So take some 3 points from set 1 and map the images. Similarly, take some 3 points from set 2, map the images. Do the same for B and observe what you can see. And for this problem, set 1 x is greater than 0, set 2 x is less than 0. Take some 3 points and find what is t of those 3 points and then map it and observe what is happening. Okay, so
Why we can take anything, right, in the second case?
yes.
Okay.
Okay, just map it and see what you are getting. I'll be back in 5 minutes. Okay. Okay, so sorry, I was expecting to come earlier. Sorry. Okay, so what is that you have observed? Anyone, can you tell your observations? So let us say we are having some point here, for example 1 comma 1. So let's say this is 1 comma 1. What is the image of 1 comma 1 for this transformation?
1 comma minus
1
comma minus.
minus 1. So it is here 1 comma minus 1. Now what about some other points? So for example minus 5 comma 2. So 1 2 3 4 5 and 2 here. So you have minus 5 comma 2 somewhere here. Okay, so what is the image?
minus 5 comma minus 2.
Minus 5 comma minus 2, right? So it is here. Okay, so just one more point let's take. So maybe let us take 3 comma 4. So it will be somewhere here, 3 comma 4. Okay, so 3 comma 4, what is the image?
3 comma minus 4.
3 comma minus 4. So what is that you observe?
The vector gets flipped about x-axis.
Yeah, so you can observe that the vector is reflected about x-axis, right? So it means you will notice that your x-axis acts like a mirror. Whatever images, vectors you take here, the images are like mirror images, considering x as your mirror, right? So this transformation T is called the reflection about x-axis. Why is it reflection about x-axis? Is it clear to everyone? Yes? Yeah? Okay. Same way, what you observe about the next transformation? What do you observe about the next transformation?
Reflection about
Reflection about y-axis.
It is a reflection about y-axis. So now your mirror is your y-axis, right? So for example,
Yes.
if I am taking 2 comma minus 2 comma 2, here the image is this, right? And then if I am taking, for example, maybe minus 1 comma minus 1, the image is here, right? And if I am taking some minus 3 comma or anything from here itself, 3 comma 4, then you see that it is 3 comma minus 3 comma 4, 3 comma 4, right? So here you see that this is your mirror now. Okay, so this is your reflection about y-axis. Okay, so geometrically also there are some significance you can see for a linear transformation. Okay, so this transformation is what you have given as an answer here. This is a just a scalar multiplication. So if your modulus value of k is greater than 1, then the transformation is just a dilation. That means the vector is lengthening. And if the modulus is strictly less than 1, it means what? The g value is a contraction. Do you understand what is happening here? So for example, in R2, what happens in R2? In R2, right? In R2, you have already seen this concept, right? In R2, suppose you are taking some vector, for example, this is the easiest to visualize. So if you are taking this vector, what happens if you take any value such that mod k is greater than 1? For example, if you take k is equal to 2 or k is equal to minus 3 or all these things, you see that mod k is greater than 1. So in this case, what happens? The vector gets elongated, right? The vector gets elongated. For k is equal to 2 also it is elongating. For k is equal to -3 also it is stretching, but in the other direction, right?
Yes, ma'am.
So
Yes,
if
ma'am.
modulus of k is strictly less than 1, for example, k is equal to 0.5 or k is equal to minus 0.75, something like this, then you see that mod k is strictly less than 1. In that case, what happens? The vector
That's it.
shrinks. So it is becoming something like this. So it
Yes,
is a
ma'am.
contraction. Okay?
Yes, ma'am.
Okay. Now just the visualization, since it is in 3D, I have given the visualization to you. What do you see from here? What is it you can observe?
Some parallelogram, ma'am.
No. Observe carefully. You have a vector here, okay? And
Yes,
this
ma'am.
is your image. This is your T of x1, x2, x3. It is here.
Yes, ma'am. Image about X plane.
Yeah, and this is your xy plane.
Yes, ma'am.
Except when is a mirror then.
Yes.
That one is a mirror.
This acts as your mirror.
Yeah.
Right? So this is a reflection map and it is a reflection about a plane now. Right? So reflection about xy axis.
Right, ma'am.
Okay? Now, what about this? Projections are very important. We will see more about projections in week 8. Week 8, correct. So, what are projections? So, this kind of things you might have seen very often in physics problems, right? You have a ladder.
Yes,
Where does the image of the ladder will fall? Some things like that, right? So,
ma'am.
you see that you have a vector. You are simply projecting it on the xy plane, right? So, this is a projection on xy plane.
X plane.
When
Right? So the z vector, z coordinate becomes 0. That's all. It is a projection on the xy plane. Right? In R2, how does the projection look? For example, in R2, so projection on x-axis, how does it look?
Projection on x-axis, then y will become 0.
X comma y will be simply projected to x
X.
comma 0. Right? Okay.
Shrinking of one axis.
Yeah. Now the rotation transformation, again, this is a very important transformation. We are going to see more on rotation in week 8 again. So what are rotation transformations? So it means what? Suppose let us say you are having some vector here. This is your vector x comma y. Okay. So in fact, this is your vector 1 comma 0 here. Let us say this is your vector 1 comma 0. Your unit vector you are considering. Okay, if this is your 1 comma 0 and now I want to rotate this vector to an angle theta. Okay, I want to rotate this vector to an angle theta. So this is your t of 1 comma 0. Same way, here is your vector 0 comma 1. I am rotating this to t of
0, 1.
to an angle theta to obtain t of 0 1. So why I'm taking 1 0 and 0 1? Because if I know where does this vectors go, then I know for any vector x comma y, right? So that is why I'm looking at the standard basis. Okay, now why is this cos, sine and 1? Can anyone tell?
Angle, ma'am, angle.
It is a projection of the uh, vector on the x and y axis.
Sorry, what?
Projection of the
Projection.
Okay, you can, you can see, you don't have to think it of projection, and I'm not going to that extent. First of all, do you see that this is a circle with radius 1?
Yes, ma'am.
yes,
So
yes,
this length is 1, do you agree?
Yes,
yeah,
ma'am.
Okay, so now this is again a circle and this is also again a radius. So this is also one that you can see.
Yes,
yes,
ma'am.
Okay, now you consider this triangle. In this triangle, this is your hypotenuse, this is your
Yes.
adjacent, and this is your opposite. You already know the value of hypotenuse. Now,
Yes, ma'am.
what is sine theta?
Sine theta.
One.
Opposite by base. Yeah,
Yes.
opposite by hypotenuse. Yeah.
Yes.
So here hypotenuse is 1. So since simply opposite side becomes sine theta.
Right.
Same way, cos theta is adjacent by hypotenuse, and since hypotenuse is 1, your adjacent simply becomes cos theta. You understand how sine theta and cos theta came?
Yes, ma'am.
Yes.
You can understand this also in a similar way. Okay. Now
Right.
you are given that this transformation t of x comma y is this. How is this cos theta sine theta minus sine theta cos theta? So now first of all, what are the coordinates here? This is, what is your x value of
Cos theta and y value is sin theta.
Sin theta.
cos theta sine theta?
Comma sin.
Same way, what about this one here?
Minus sin theta and plus cos theta.
Yes, this one will be minus sine theta. If you look at the details, you will understand why it is minus sine theta. This
Yes,
is
ma'am.
minus sine theta and cos theta. These are
Right.
the coordinates. Okay. So
Yes.
now we have seen what is t of 1, 0 and t of 0, 1. Okay. Now, how does this matrix really make sense? Just for and more deeper understanding, just let us consider the simplest case, theta is equal to 90. What happens when theta equal to 90? Where does 1 comma 0 goes to? If you
0, comma 1.
1
0, 1.
0 comma 1, how can we visualize it from here? Can you see what is cos 90?
0.
0,
What is sine 90?
1.
So what happens to this matrix?
0 minus 1
0. 0 minus 1.
1 0.
0.
So now what is the multiplied vector here? 0 1.
0. Yes.
0 1.
Can you see that 1 0 is mapped to 0 1?
Okay.
Got it? Same
Yes.
way,
Yeah.
where will 0 1 get mapped to?
It will map to 1, comma 0. Minus 1, comma
0.
Okay, let's check that as well. 0 comma 1, 0 minus 1, 1 0. You can see that.
Into 1. Into 0 1. Yeah.
0, 1.
So you see that this is mapping to minus 1 0.
0.
Clear?
Yes.
Okay, fine. So this is a rotation transformation. Okay, how we got this? Is it clear?
Yes,
Yes.
ma'am.
Okay, fine. So these things, the geometrical aspect, this is for your visualization. The geometrical aspect does not really appear in your quiz, but it helps you to have a better understanding. That's why I have provided it here. I hope it will be useful to you. All right. So the next important topic here is that you have seen what are 1-1 functions and onto functions in your Math 1 course. How many of you remember it? What is a 1-to-1 function? What was an onto function? Bijective functions?
Yes,
Yeah,
ma'am.
If
yeah, you
Yeah,
have.
bijective function there.
So we are going to quickly recall 1-1 and onto functions, and then we are going to see the same 1-1 and onto concept for transformations. Okay. First of all, if you have a function f from x to y, so you know that x is called the domain and y is the codomain.
Yes,
Right?
ma'am.
And for an x in x and y in y, if f of x is equal to y, we call y is a image of x under f, and x is a pre-image of y under f. What is the image and pre-image? Is it clear? Yeah.
Yes, ma'am.
Now a function is called injective if there are no two elements from the domain which map to the same image. It means what? Suppose you are having two different elements. Okay, then f of x1 and f of x2 cannot be
So
same.
unique. Yes, ma'am.
Okay, so for example, consider this function f of x is equal to x squared. What happens to f of 1?
Minus 1 and
F of 1 is 1. F of minus 1?
1.
1.
is 1.
So f of 1 and my f of minus 1 are same. So this says that f is not,
not
1,
1.
1.
yeah, it is 1-to-1. Injective, another name, injective. Right? 1-to-1, injective are interchangeably used, not injective. Okay. Now a function is called surjective if every element of the codomain of the function has a preimage. Here I should give an example for injective also. So f of x is equal to 2x. You take, so you take you take two distinct elements x not equal to y, and 2x not equal to 2y. So this is 1 to 1, right? So now what is surjective? So you have f from, so you have x, domain x, domain y, right? So you have a f. Now what are all the images of x? Range of f is a set of all images, right? So set of all f of x, x is in x. This is your range, right?
Yes, ma'am.
Yes.
You always know that your range is a subset of
Codomain.
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 Okay. Now surjective means if f of x is equal to y, that is your range is your entire codomain, then you call the function to be surjective. Okay. Another way to
Yes.
say is that for every element here, you will be able to find a preimage.
Yes, ma'am.
Okay. For
Yes.
every element of the codomain, you will be able to find a preimage. Okay. So these are the definitions you have already seen in math 1. So this is a general definition for one-to-one and on-to functions. Now let's look at the exact same definition for transformation. It's exactly the same. Nothing will differ. So a linear transformation T from V to W, where V and W are vector spaces, is called a monomorphism. Just the name is a fancy name is given, monomorphism. It is just one-to-one transformation. Okay. If T is an injective map from V to W, that is T of V1 equal to T of V2 implies V1 equal to V2. So see, one to one, there are so many different ways to say the same condition. So one way to say this is you can say V1 not equal to V2 implies T V1 not equal to T2. This is one way. Or you can say TV1 equal to TV2 implies V1 equal to V2. There is one more way. Does anyone know? There is one more way that is only for actually linear transformation. So if TV is equal to 0, can anyone say this condition is only for linear transformations? If TV is equal to 0, what should be for an injective function?
V equal to 0.
Yes. Why is that so? What do we already know about a linear
T of T
transformation?
of T of 0 is 0.
Yes.
So in that
T of 0 is 0, we already know. So it means if T is injective and T of V is 0, then V should be 0. Okay. So these are three different ways of saying T is 1 to 1. Clear? Okay. All are equivalent definitions. For linear transformation, this is only for linear transformation, particularly this one. This two is applicable for functions also, but this is particularly for linear transformation. Okay. Now,
yes, ma'am.
the surjective definition also goes exactly the same way. The range of T, that is the set of all TV such that V is in V, this set should be equal to what? Can you tell?
W.
Yeah. Okay. So this set should be equal to W. Or what is the other way? For each W in W, there exists V in V such that TV equal to W. So that is there exists a pre-image. So your V is your pre-image of W. Clear?
This is surjective, right?
Yeah, this is for surjective. Okay, so these are conditions for one-to-one. These are conditions for on-to. Okay, fine. And if both the conditions are satisfied, that is, if T is both one-to-one and on-to, you call it an isomorphism. This word isomorphism is important. I did not stress too much on these two words, but isomorphism, this is very important word. Okay, so if a transformation is both one-to-one and on-to, then it is an isomorphism. Okay, this has lot of important properties. We will look at it in the upcoming weeks. Okay, fine. Now first, everyone take paper, pen, check one-to-one and on-to. I will tell you how to do maybe for one problem, then you can do it for the other problems. Okay, one-to-one is very easy to check. How it is easy to check one-to-one? So for example, T of,
Just put 0, right?
yeah, T of x comma y is equal to 0, 0. If, so let us say let T of x comma y is equal to 0. Then what happens? 2x comma y is equal to 0 comma 0. This implies your x comma y is 0, 0. So T is 1-to-1. How will you check on to? How will you check on to? So let us say you are having any real number. Let us say alpha is any real number. Can you write your alpha in terms as 2x for some x in R? Can you do this?
Like we have to just check whether the function outcome is span of the codomain, right? Like that.
Sorry, what you want to check?
Like whether the outcome
Mhm.
is a span of the codomain, right? Something like that.
It's actually, you should actually check the range is the entire R2. That is what I am trying to do here. So entire R2 means what? The first coordinate should be any value R. Okay. So I
Hmm.
want to see whether your alpha comma beta. Okay. So this is all the set of all alpha comma beta in R2 is same as set of all 2x comma y. Is this same? I am trying to check. Those who know that it is already same, it's fine. For those who don't know, I'm explaining. So, can we write any alpha as 2 times of x? Tell me what's your answer?
Yes.
Yes.
Yes, right? So, just simply take x is equal to alpha by 2, you know, right? Same way, can you know y is equal to beta. So, you have t of, if you take alpha by 2 comma beta, you will get alpha beta. So, for every alpha comma beta in your codomain, you have the pre-image. So, this is your pre-image. You are able to find a pre-image for every element in your codomain. Okay, now B part I am giving it to you. Let's see how many of you are able to do it correctly. So here the answer is T is onto. So T is both one-to-one and onto. So therefore T is bijective.
B is only onto.
Okay, B is only onto. Okay, first of all, how many of you agree with his answer?
It is also 1, 1, right?
How many of you agree with this answer? I don't see any response. Only one, only onto. All your answers are wrong. Okay, let's see how you have.
Now it will be 1, 1 for sure, right? Because if you just put 0, then
No. Okay, let T of x comma y equal to 0 comma 0. What is that you will get? 2x comma 0 is equal to 0. This means x is equal to 0. What about your y? So what is t of 1 comma 1? Or let's say 0 comma 1. What is t of 0 comma 1? What is your answer?
0.
0.
So you have a non-zero vector which is mapped to 0, 0. Is it 1 to 1?
No,
No.
ma'am.
No, right? So it means
No.
you
No.
see this is
Got it.
not 1 to 1. Clear? You
Yes,
should
ma'am.
get this vector completely 0. Then only it is 1 to 1. Here, what about y is not sure. So you try with some non-zero y and see what happens. You see that you are still getting 0. It means it is not 1 to 1. Clear? Okay. Now what
Yes, ma'am.
about the
Ma'am,
on?
please explain once again.
Okay. See from
Ma'am,
here.
since it is,
Yeah. Tell
ma'am,
me.
since it is two images, uh, then it is not even a function. Or
No, 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 no. See, for a function, one element should not have two images. Two
yes, ma'am.
elements can have the same image. Here you are having two different elements having same image, that is acceptable for
Okay.
a function, right?
Okay.
So for
Yes, ma'am.
example, here v1 is 0, 0, v2 is 0, 1, right? v1 is not equal to v2, but tv1 equal to tv2. Both are 0, 0. So this means
Yes, ma'am.
T is not 1 to 1. Clear?
Yes, ma'am.
The girl who asked, is your doubt clear?
Yes, ma'am.
Okay. Okay. Now what about the onto part? The onto part, you are having t of x comma y is equal to 2x comma 0. So what about, can you find a pre-image for 1 comma 1?
Ma'am, but according to the problem, it should be 1 comma 0, or I mean of that form, na ma'am, because we are not looking out for everything.
But I'm just for me the condition is that my range should be, I can take any element in the codomain and look for a pre-image. That is the condition for
Wouldn't
all.
that be restricted by the transformation, ma'am?
No, it is restricted by your codomain only.
Okay,
The
okay.
definition is that for every v in w there exists a v in v such that t v equal to w. There is no restriction on what is your t. Does not matter. That is why it is the definition of surjectiveness, right? So here I am going to take any element from my R2. This is some random element from R2. So any random element, if it has a pre-image, then only it is a onto function.
Onto function. Yes, ma'am.
Does this have a
No,
pre-image?
no, ma'am. No, it doesn't have.
So for t of x comma y cannot be 1 comma 1 for any x comma y, right? So t is not onto. In fact, what can be the range? The set of all 2x comma 0. What is this set exactly? Can you tell?
The x-axis.
X comma.
It is simply the x-axis. It is not equal
Yes,
to
ma'am.
r,
X axis.
Yes,
right?
ma'am.
Only if it is
Yes,
equal
ma'am.
to r2, this set is equal to r2, you know that it is onto.
One, two.
Now everyone
Ma'am,
try
so
this.
for problem like this, we do not map the linear transformations, the value of r over there to the r which is specified for the inputs.
Sorry, I don't get your question.
In the linear transformation, it says t of xy is equal to 2x comma 0. So
Yes.
I do not have to take that 0 and put it to r2 over there just by thinking that I will not take anything other than 0.
See, your range is restricted to the second coordinate being 0.
Yes,
But your codomain is not restricted to it. Your
right, right,
codomain is specifically given to be R2.
correct.
Okay. Fine. Now everyone check it for C. Option C.
Can you just show the question once again?
1 minute. Yeah.
Ma'am, bijective.
How many of you agree with this answer?
Okay,
Yeah.
sorry.
Ma'am, it
Not,
won't
not,
be
not
bijective, but
bijective.
at
Yeah.
least T is
One
onto.
one.
Surjective is there.
Okay. Okay, let's check then. Okay, fine. So you have T of x comma y comma, let T of x comma y comma z equal to 0 comma 0. Right? It means that you have x comma y equal to 0 comma 0. So this implies x equal to 0, y equal to 0. Now what happens to z? So how will you check? Take 0 comma 0 comma 1. What is the image? What is the image?
0, 0.
0,0.
0, 0.
So it means T is
Oh,
Not,
sir.
Not one.
Not
not
1.
1
Not
1.
1, 1. Yeah.
T is not 1 1. Okay, fine. What about the surjective part? So you have T of x comma y comma z equal to x comma y. So the set of all x comma y in R. So what is this set? This set is nothing but exactly.
R2.
This is exactly R2, right? So set of all T of x comma y comma z, x comma y comma z in R3 is this set, which is R3. So if it is R3, what can you conclude? T is
Surjective.
onto, right? So this is your range, this is your codomain. So range is equal to codomain implies T is onto. Clear? Okay, now check it for D.
Excuse me, ma'am.
Yes,
Please explain once again that part.
this one.
Yeah, I didn't get the range is equal to codomain.
See, what is your range defined? How is your range defined? Range is set of all T of x comma y comma z for all x comma y comma z in R3. Now, what is T of x comma y comma z? It is simply x comma y, right? Where x and y are in R. Now, sorry, this is not R3. Sorry. No one told it to me. This is R2, right? Yeah. So now what is set of all x comma y such that x comma y in R? What is this set equal to? This set is nothing but the definition. This is the definition of R2. So now here you see if your range is equal to the codomain, then it implies that your transformation is onto. Clear? Yes?
Yes,
Yeah,
ma'am.
ma'am. Now clear. It's R2 because I was confused that you are wrote R3 and then how you are.
Yeah. It's good that
Yeah.
you pointed it out. Thank you. Okay. Now what about the D part?
Onto one, but not onto.
Not onto. But
Okay. So now it's clear that T of x comma y is x comma y comma x plus y, which is, sorry, first of all, let me write it as 0, 0, and then I will equate it. So let T of x comma y is equal to 0, 0, 0, which implies x comma y comma x plus y equal to 0, 0, 0. So simply I will get x is equal to 0, y is equal to 0. So the domain vector here has become 0. So what can you conclude? T
T of
is
0
1 to 1.
onto 1.
Right? Now, the next thing is that you want to check the range. What is the range? Okay, will the range be entire R3 or not? Now, for example, consider this vector. Can you find a pre-image of 1, 2, 4 under T. So it means what? Can you find x, y such that x, y, x plus y is equal to 1, 2, 4? Is this possible?
No, ma'am.
It's not possible, right? Here 1 plus 2 is not, here this 4 is not 1 plus 2, right? So it is
Yes,
not
ma'am.
in this format. So it means what? Your 1, 2, 4 does not belong to your range of T. So your range of T is not equal to entire R3. So T is not onto. Clear? Why it is not onto? Is it clear for everyone? I found an element for which there is no pre-image under T. Clear? Yes?
Yes, ma'am.
Okay, fine. All of you are
Ma'am,
done.
can you, for the D option,
Yeah.
can you please repeat the last step, ma'am? The 1 to 1. I know that x equal to 0, y equal to 0. The fourth option, ma'am. The fourth option, the t is 1. So here from x equal to 0, y equal to 0, till that part I understand. After that, how we are saying it is 1 to 1?
Oh, see, for 1 to 1, what is that we need to show? TV equal to 0 implies V is equal to 0. This is the condition for 1 to 1. Your V, this is your V now. Okay, so if your x is equal to 0, y is equal to 0, then it means your V is 0.
Okay.
So you have proved this condition.
Okay.
But in the previous cases, you see that we are not able to prove that your V is 0 because we don't know anything about the third element.
Yeah, Z, yeah.
Clear?
Yes. Okay.
Okay. So already now you have a clear understanding about 1 to 1 and onto functions. Can you all quickly answer this question here? So choose the correct set of correct options. This is a very easy one. T is a 1 to 1 linear transformation if and only if there does not exist any V non-zero such that T be equal to 0.
So false.
See, understand the statement clearly.
True. Yeah.
There does not exist any V non-zero such that T be equal to 0. It
True.
means what?
Oh,
Only
true.
0 value be mapped to 0. True,
Yeah,
right?
only 0 has to be mapped to 0.
Yeah. What about option 2?
False.
Can you give an example? We have an example here, I guess. Where was the example? Yeah. So this is
The
both
first one is-
1 and 2, right? So here you see that T of x comma y is equal to 2x comma y. This is the example we saw. This is both surjective and injective.
Yes.
So this is incorrect.
Hmm.
What about option 3? Okay, first of all, to answer this, before answering this, I have another question. What is the general form of a linear transformation from R to R? How will you write? So you take a V from R. What is T of V?
T of x equal to a into
Alpha times V plus beta.
Please think again and tell. T of V is equal to?
a into v.
Yeah. A is some real number again. Right? Okay. So this is a general form of a linear transformation from R to R. So now you are given the T from R to R. So it is of this form. Okay. It is a linear transformation. It is going to be of this form. Also, it is given that it is not injective. What is mean by not injective? How can you write the definition of T is not injective? See, T is injective means you know that TV equal to 0 implies V is equal to 0. Now, T is not injective. What does that mean?
TV is 0 given that V is not equal to 0.
So, we can find a V in V such that V is not V non-zero in V such that TV equal to 0. Correct?
Yes, ma'am.
Okay. So now we are having some non-zero V. Okay, non-zero V for which TV equal to 0. So instead of V, maybe I will write U so that I don't get confused with this V here. Okay. There is nothing wrong, but just to avoid confusion for some students. Okay. So this is the condition. Now let's say that you are having U non-zero. Okay, and T of U is equal to A times of U, and
Yeah.
this is equal to 0. Now what is given to you? Then T must be 0. Your U is non-zero. Look at this. Your U
A
is
has
A
non-zero.
has to be 0.
So A has to be 0. If A is 0, then what about your transformation?
all are for
All
all V
all
equal
V
to
equal to 0.
Right? So it means for all V in R, so this means that your T is a 0 transformation. Correct?
correct.
So that is that what given to you?
Yes.
Yes.
You all understand?
Yes.
Clear? Okay. Now look at option 4. If there exists some non-zero vector V in V such that TV equal to 0 for a linear transformation T from V to W, then T cannot be an isomorphism. First, let's read the first statement again. If there exists some non-zero vector V in V such that TV equal to 0. What does this tell you? V non-zero
True,
and equal to 0. So first tell me what does this imply?
not
Not
injected.
yes.
Yes, T is not injective. So if T is not injective, you know that it cannot be isomorphism. So it is correct. Okay. So all the options are clear for everyone? Yes? Okay.
Yes, ma'am.
So how many more problems I have? Okay. I just have, this problem is already done. So only 2 more problems left, or maybe 3 more problems. So I will do one thing. I'll give this and this as a homework. I will do the middle one because middle one is an important one which involves some properties. This and this as a homework. If you have doubts, you can discuss this in the TA session. I want you to all just listen to this last question and then we can stop, because this is kind of summarizing the properties we have seen so far from week 1. Okay. T from R3 to R3 is a linear transformation defined as follows. Okay. Now TV is equal to AB. This is something which you already know. Now T is injective if and only if the system of linear equation AB equal to 0 has a unique solution. First of all, what is the meaning of T is injective? Tell me.
T of 0 is 0.
0 vector
TV equal to 0
V
implies
V equal to
V
0.
equal to
0.
0. Now what is the meaning of the second part? So the second part is that the system of linear equation AB equal to 0 has a unique solution. This means that, so the set AB equal,
If
set of
the
all
solution is the only
equal to
Linear
solution.
solutions.
So it means that AB equal to 0 implies V is equal to 0, right?
Yes.
The solution of this is V equal to 0, correct?
yes
Yes.
So are they same? Because TV equal to AB,
yes
Yes.
right? Okay.
Yeah.
Now T is injective if and only if rank of A is equal to 3. Now you see that if T is injective, we already saw that this system has a unique solution. Now when does this system have a unique solution? This is a 3 by 3 system. When will this have a unique solution?
Determinant is not equal to 0.
Determinant is not equal to 0.
So T is injective tells us that AV equal to 0 has unique solution. This tells us that determinant of A is not equal to 0, and this tells us rank of A is equal to 3. Yes or no?
Yes.
Yes.
What about the other direction? The same. If rank of A equal to 3, you know that determinant is non-zero. You know that if determinant is non-zero, AV equal to 0 has a unique solution. Then you know that this implies this. Both the directions are clear? Yes?
Yes.
Okay. If the system of linear equation AV equal to B for any B in R3 has a solution, then
Ma'am, please explain option 2.
Okay. In option 2, from option 1, we know that if T is injective, then AV equal to 0 has a unique solution. Okay, this is from option 1. And then if AV has a unique solution, we know that actually these are two-way equivalent conditions. And also we know that if AV has an equivalent solution, it is if and only if that the determinant of this matrix is non-zero. And the determinant is non-zero if and only if rank of A is equal to 3. So we have the two-way proof for T is injective if and only if rank of A equal to 3. Clear?
Okay, ma'am.
Fine. So option 3, you just have a rewritten version of the definition of surjective. What is the definition of surjective? For any V in R3, right, there exists some X in R3 such that TV is equal to, Tx is equal to V, right? So here in place of B, I have V, and here this X is your solution of Ax is equal to B, correct? Right? So this is just rewritten version of this. Do you all see that? So every element in the codomain has a pre-image. So the same thing is written in terms of the system of linear equation AV equal to B. So AV equal to B is some other version of TV equal to W. Is that clear? Maybe I will use the same W and everything so that you don't have any confusion. So TV, this is W, this is V. So TV equal to W. Clear? Yes or no?
Yes, ma'am.
Okay. Fine. What about the last option? T is not surjective, then there exists some B in R3 such that this has no solution. It means this has no pre-image. What does this mean? What does this mean? This means that this has no pre-image. This element has no pre-image under T. Correct?
Yes, ma'am.
Yes, ma'am.
So it is not surjective, it is correct. So this is correct, this is correct, this is correct. All are correct options. So this is kind of summarizing all the properties which we have seen from the beginning, and it is also giving us a combined relation between all the topics we have seen so far. So that's why I wanted to do this one today. I hope this is clear for everyone. So all the topics which we covered today, is it clear for everyone? Yes, we have completed 5.
Yes, ma'am.
Okay.
Yes, ma'am.
So then do the homework, do 2 problems which are given as homework. Okay, and if you have doubts, you can discuss in the TA session.
So, ma'am, week 5 is complete, right?
Yes, complete. Okay.
Just today, the YouTube will find this session.
Of course, I'll just share the link if you want. Just a minute.
Okay.
Okay.
Thank you.
The chat. Okay, fine. So let's wind up then. See you again in the revision session maybe. Okay, week 6, Sanidhi will be handling. All right. Okay then. See you all.
Okay, ma'am. Thank you.
Okay,
Thank you, ma'am.
Thank you, ma'am.
Was there any improvement in your